This is the fourth in a series of resources on limits. We consider the basic idea of a limit and provide a formal mathematical definition for a limit. We look at three instances where a limit does not exist. We explore various properties that make finding limits simpler and look at multiple examples. We consider what it means for a function to be continuous as it pertains to limits. We close the series by considering infinite limits. What does it mean to be continuous? In the real world, we think about amounts that have no gaps or breaks. For example, we think of time as a continuous quantity, as opposed to something like shoe size, which are discrete measurements. When we consider functions, continuity takes on much the same definition. The general idea of continuity for a function is that the graph has no breaks, jumps, or gaps. We can draw the entire graph without removing our pencil from the page. But what is the formal definition for continuity? A function must meet three criteria to be considered continuous at some point C. First, the function has to be defined at C. This means there are no holes in the graph. Next, the limit as x approaches C for f of x must exist. The graph must approach the same real value from both the positive and negative directions. This means that there are no jumps or other gaps in the graph. Finally, the limit as x approaches C for f of x must equal f of C. Again, we cannot have any jumps in the graph. Let's look at examples of graphs that fail these three criteria. If we inspect this first graph, we notice that there is a hole in the graph. At x equals 1, this function is not defined. Since the function does not meet the first criteria, it is not a continuous function. The second graph is defined for all values. However, the graph approaches different values from the left and from the right as we approach x equals 1. Therefore, the limit as x approaches 1 for this function does not exist, and the function is not continuous. One final example is this third graph. Again, the function is defined for all values, and the limit as x approaches 1 is defined, but the limit does not equal the actual function value at 1, so this graph is discontinuous. Let's discuss these discontinuities. Let's assume the function is continuous everywhere except at point C. The discontinuity can take one of two forms. Either it is a removable discontinuity or a non-removable discontinuity. A removable discontinuity can be fixed to where the function becomes continuous in one of two ways. We could fill in a hole in the graph by defining the function at that point of discontinuity, or we could redefine the function so that the limit as x approaches C equals the function at x equals C. Let's look at the examples from earlier and determine what type of discontinuity each possesses. This first example is not defined at x equals 1. However, the limit does exist as x approaches 1. This is a removable discontinuity. If we define f of 1 to equal 1, we fill in the hole in the graph, and this function becomes a continuous function. In this second example, we have a situation where the limit does not exist because the limit from the left is not the same as the limit from the right. This is a situation where the discontinuity is non-removable. For the final function, again we have a well-defined limit as we approach 1, but the actual function value does not equal the limit. Again, we have a removable discontinuity. the function becomes continuous if we redefine f of 1 to equal 1.